This was not possible 30 years ago. Capturing vivid imagery of cryptic organisms at and beneath the ocean floor. And that's what we do. We use innovative technology to image the seafloor.
But we don't just take pictures of the seafloor.
That's true, Steve. We use these images to make quantitative analyses that allow us to better understand the functioning of the seafloor within the larger perspective of the ocean.
And then we use the data that we collect to make innovative data visualizations that allow anybody, not just scientists like ourselves, access to this unique and interesting ecosystem.
But wait, Steve. Let's take a step back. Before we delve too much into the innovative work that we do, it's important that people understand how critical the ocean and the seafloor are for the speck of space dust we call our planet. We humans are terrestrial creatures, and as a result, much of our perspectives about the Earth are shaped from our interactions and visual observations on land. However, when we take a step back and look at the Earth as a whole, we realize that the Earth is a pale blue dot. And that's because despite our terrestrially centric mindsets, much of our planet is covered by the ocean. Given the vast spatial extent of the oceans on Earth's surface, it should come as no surprise that this vast body of water plays a key role in life on our planet, including the lives of humans. Ocean processes influence all of humanity, whether residents of the coast or inland, via the regulation of climate, local weather patterns, economic impact, and food security, among others. We are inherently dependent on the health of a global ocean ecosystem, which, beneath its surface, exists at a far greater scale than is visible on a globe. And at the very bottom of the ocean is the seafloor, a predominant habitat serving a variety of functions and hosting its own brand of unique and interesting life. If the oceans cover 70% of our planet, then inherently 70% of the Earth's surface is the seafloor. And in the larger scheme of the ocean, the seafloor holds great importance for ocean health. The seafloor is home to many unique and diverse environments such as seagrass meadows, kelp forests, vent communities, and coral reefs. These dynamic areas serve as safe haven nurseries for young ocean life and contribute greatly to ocean productivity. However, despite their well-documented importance, these habitats are not the predominant bottom type of the seafloor. Coral reefs make up less than 0.1% of the total ocean bottom. To put that into perspective, that's roughly half the size of the country of France. And combined, coral reefs, seagrasses, and kelp forests make up less than 1% of the total seafloor. So what else is there? What makes up that 99%? Most of the seafloor looks something like this. It's a habitat of soft sediment that's largely composed of small-scale features such as tubes, burrows, and mounds. But despite this relatively muted appearance, this large area of Earth's surface holds huge importance for the functioning and health of the ocean. Think of the soft-bottom seafloor as the lungs of the ocean. These areas serve as a sump for ocean pollutants and a recycling plant for ocean nutrients. It's easy to conceptualize the importance of seafloor environments such as kelp forests and coral reefs because we can easily visualize the complexity and diversity of the structures and organisms that exist there. However, when we compare those areas to the soft-bottom seafloor, while there are some features on the seabed, most of the structural complexity exists beneath the opaque surface of the seafloor, making this cryptic environment notoriously difficult to observe. But if you're fortunate enough to peek beneath the seafloor, you observe a dynamic world full of complexity and diversity, one which is often not immediately obvious when viewing the seafloor from only the surface. The best way to think about what you're seeing is to imagine you're at the bottom of the ocean and you're peering into the seafloor from a profile perspective, analogous to as if you're holding up an ant farm and looking through the side. And when you look beneath the seafloor, you see animals burrowing through and excavating the sediment, tubes being formed and destroyed at the seafloor surface, and a number of physical and chemical changes occurring in the sediment column. We can see from the changing colors in the sediment that as these animals weave their way through the sedimentary fabric, the influence and effect that they have on sediment quality. Think worms in a garden, to put it into a familiar context. So we know that the seafloor is important, but what are the methods that we employ that allow us to better study and understand this environment? Most of the seafloor exists at ocean depths that are far greater than that with which we can send a diver down to. And very little ocean science actually involves physically sending someone down to the bottom. To overcome the fragility of the human body, the development and application of remote sensing techniques was a necessity in order to better understand this important environment. For 150 years, we largely sampled the seafloor blind. Traditionally, if we wanted to understand what was going on with the animals in the sediment, we would have to collect a sediment grab. And lead lines would be lowered to the bottom and the length of the line documented to determine the depth and topography of the seafloor. These methods are reductionist and offer very poor resolution. But advances in technology have allowed us to make a more holistic assessment of our seafloor observations. Single beam and more recently multi-beam sonar offer much higher resolution imagery of the depth and topography of the seafloor. And the development of the sediment profile imaging camera, or SPY-CAM, allows us a more clear picture of what's going on with the animals in the sediment. Now, I've already shown sediment profile images in this talk, but to give you a better sense of how this system works, as the SPY system is lowered to the seabed, a weighted trigger activates the camera, capturing a plan view image of the seafloor. The system continues to descend until contacting the bottom. Upon contact, tension is released from the cable, allowing a weighted camera prism to lower and penetrate the seafloor. An undisturbed profile image of the sediment column is captured, allowing scientists to document biological activity, chemical processes, and physical changes at and beneath the ocean floor. The huge benefit of this technology is that it allows us to document and observe the functioning and behavior of the organisms without removing them from their habitat, the seafloor. And when we do that, we're able to make really distinct observations about seafloor health. Typically, healthy seafloors are characterized by a rust red-brown color that extends deep beneath the seafloor surface, indicating these areas are oxygen-rich and contain large and diverse life. By contrast, unhealthy seafloors are a dark gray-black color. These areas contain little to no oxygen, lack diversity, and have very little to no large organisms. Now I could show you a graph or table indicating why the seafloor to the left is healthy and why the seafloor to the right is unhealthy. Or I could couple that data with images and make that point much more succinctly. And that's what we do. We take our quantitative data and we pair it with images and we give people a better understanding about how the seafloor is functioning. When we do that, we're also able to assess how the seafloor responds to and recovers from disturbance. This movie is depicting an area of the seafloor that's experiencing what's commonly known as an ocean dead zone, or an area of the sea bottom where there's little to no oxygen. And when oxygen is removed from the seafloor, bacteria take over. The bacteria are the filamentous white lines you'll see moving through the sediment, on the seafloor surface, and on the faceplate of the prism. These bacteria are thriving during this ocean dead zone, which is prohibiting larger organisms from surviving. And you can tell how happy the bacteria are by the amount of organic matter they're producing, which you can see sloshing down on the faceplate of the prism. So, over time, when oxygen returns to the seafloor, these bacteria scurry back down into the sediment, and these areas will be repopulated by larger organisms such as worms, clams, and crustaceans.
This profusion of new technology has led to a flood of data that we can now mine, such as the example that Kersey just presented.
Well, Steve, we are, after all, visual organisms. And the true power of this technology is that it allows us to present our work about the seafloor in a format that everyone understands, a picture. Now, in the past, when we would send our equipment down and explore some new area of the ocean, we would recover it and then spend weeks, months, sometimes even years combing through this data by hand, eventually compiling it together into thick, bound reports like this. I think my friend Steve Heath could recognize that if you're trying to explain something about the seafloor to someone who doesn't have a PhD in ocean science, this probably isn't the best way to do it. These are important for scientists and regulators because it has information relating to our field methods, complex explanations of chemistry, but when it comes to a narrative device to tell a story about our oceans, they fall tragically short. And even worse, when these documents are delivered to a client, they sit in an archive, on a shelf, gathering dust, locked away from people that might be interested in the information that they contain. I mean, I do this stuff for a living, and I don't want to read this. Kersey, do you want to write this? Not in the least bit. I didn't think so. In 1998, one of our TED forefathers named David Gallo presented a talk in Monterey. During this talk, he showed us some wonderful video that come from his Alvin and Jason submersibles. He showed us bioluminescent jellyfish, giant sulfur vents at the bottom of the seafloor spewing gas from the Earth's core into the ocean. He showed us giant tube worms that colonize these sulfur vents. But one of the really interesting things that Gallo hit on happened when he was showing us a 3D reconstruction of the seafloor and one of his submersibles driving through it. David said that he wanted to take this seafloor environment back to the laboratory because right now we see it in bits and pieces. We see it either as sound or as photographs or as video or as data from a chemical sensor, but we haven't yet put it together into one interesting picture. And that's exactly what we're trying to do. Instead of seeing the pages from some report, we want to show people the synthesis of that data. Because as it turns out, flipping through pages of a report, cross-referencing figures, tables, different data points and charts that we've printed, it's not the most intuitive way to explore something as vast or complex as the seafloor. Now, traditionally, we would print maps and use these as a storytelling tool. We'd present them next to charts and data and captions and maybe have a little paragraph next to it explaining something about this map. But it wasn't very interactive. So here you see a map of Massachusetts Bay, just north of us. And instead of just placing the data down next to it, we've made this map interactive so that I can click on different areas in it, and I can see where we've sampled. And I can see those sediment profile images that Kersey discussed with us earlier in context. I can see them next to biological, chemical, geological data. I can even see shipwrecks, and I think that's pretty cool. This sort of visualization has served as the workhorse for our analysis team. It serves as the primary storytelling tool for us to explain our findings to an audience. But it falls short because it's 2D. And as we know, the seafloor is not a two-dimensional flat surface.
And certainly, the volume of water that sits on top of the seafloor is not flat. In fact, it's 2 miles deep on average across our globe. So what we've done here holds a lot of potential because it allows you to see in context the contours and ridges in the ocean. It allows you to see things in 3D and make connections that you might not otherwise do. And it contains all the same data that our 2-dimensional map did. But it allows us to go beyond that and go into the 3rd dimension. It allows us to draw the picture upwards and talk about the water column. It lets us see temperature differences from the top to the seafloor. It lets us see changes in salinity, which is essentially the saltiness of the ocean. And the really cool thing about technology like this is that it's built using basic and common building blocks, things that you can find in your web browser. So I don't need to spend thousands of dollars on an expensive computer system. I don't need to buy complicated software licenses. I can just look at it. Much like Google Earth, I can just pull up a web page and see it. I can even bring it up on my phone and see it on the go. And if I'm really clever, I can bring it into a virtual reality framework. Looks like Kersey's exploring the seafloor on the TEDx stage right now.
Whoa, wave of the future, dude. As you can see, this is a truly immersive experience. This is important because we can now put our data in the hands of the interested citizen. No longer are we content to allow our efforts to sit on a shelf and collect dust. That information can now be made public for anyone interested to explore for themselves, bringing a dark and mysterious world into clear focus wherever you are.
We love showing people this habitat, but bringing them down to the bottom of the ocean in person is an expensive and dangerous endeavor, and it's likely most of us are not going to go there. But now I'm proud to say that by using advances in technology, we can bring that mysterious ecosystem back up to you. Thank you very much.